Well, this question could be seen as easy to some and hard to others. What we have is a large spherical balloon which is deflating. The next sentence tells us that we've got time in seconds and the balloon's radius in centimeters and the volume in cubic centimeters. The other information that we're told is that the volume of the balloon is modeled as decreasing at constant rate. Well, because it is after all deflating, so it is decreasing. So in our first question, we're saying use this model to show that the dr over dt, and what we would do is read this as the change of the radius over the change in time is equal to minus k over r squared, and k is supposed to be a positive constant. So what we really have in here at the first is we've got time, we've got radius, and we've got a volume. So there are three variables. Let's look at those three variables first of all. So we've got t, r, and v. Now v can be related to time, and we could say that there is a change in volume over the change in time. Also, v could be related to radius, where we could say that the change in volume is related to the change in radius. Now, lastly, we could say that the radius is related to the time, and we could say that the change in radius is related to the change in time. Now, dr on dt is already given to us, and we're told that dr on dt, or the change in radius over the change in time, is negative k, which is a constant, over the radius squared. And we've got to show that k is a positive constant. So can I express dr over dt in a different way using these two expressions? All right, I have dr in this expression, and I also have a dt in this expression here, except that they're both in the denominator. That's not a problem. If I was to rearrange dv over dr and reverse it, I can multiply the two together. In other words, dv over dt, and if I multiply this by dr over dv, I will be able to get dr over dt, because the dv and the dv cancels out. So on the basis that we know that dr over dt is equal to dr over dv multiplied by dv over dt. But do we know what these are? Okay, let's go back to our change of volume over change of time. We were actually given that information that the volume of the balloon is modeled as decreasing at a constant rate. So that means that as time goes by, the volume is decreasing at a constant rate. So we must write here that it is decreasing at some constant. Okay, now what about the next expression where we've got a change of volume over the change of radius? Let's go and make ourselves a special room for this, and I'm going to draw it here. All right, so what is volume? Volume is equal to, of a sphere, The volume of a sphere is 4/3 pi r cubed. So this is just a equation, or you might say a function, where volume changes with respect to the radius. If we want to find the rate of it, then we need to differentiate it. So therefore, by differentiation, you know how to differentiate. dv on dr is therefore going to be, we're differentiating now. So that means that 3 is being put in front, and it's 4/3 pi r squared. So the 3 cancels out. Therefore, dr over dv is going to be 1 over 4 pi r squared. If this is now substituted in our equation, dr over dt is equal to 1 over 4 pi r squared, and we're going to multiply it by a minus constant, and this will become minus c over 4 pi multiplied by 1 over r squared. This would be clearer if I just wrote c over 4 pi and then I multiplied it by minus 1 over r squared, which means that k now is equal to c over 4 pi. So I'm here to show you exactly how to do this, to explain this to you. If you are at the exam, you of course do not need to put so much detail, but you're getting 3 marks for this. So one of the things you will need to do is to make sure that you have this equation in dv over dt is minus constant, that you also have what's in here in this box, and that what you have also is in this box, and finally you will need to have the answer to k. And this was a solution to A. And for B, we are given that the initial radius of the balloon is 40 centimeters. After 5 seconds, the radius of the balloon is 20 centimeters. And thirdly, we're given that the volume of the balloon continues to decrease at a constant rate until the balloon is empty. So we're solving the differential equation to find the complete equation linking the radius and the time. Notice that it says you have to solve the differential equation. That equation is this equation here. And if you want to find the equation itself, we need to do some integration. By integrating the above, we'll be able to find a complete equation which links r and t. If I cross multiply this equation, I will get r squared dr, which is equal to minus k dt. So I've moved the differential of the radius together with the radius squared. Now it's easy to integrate this and this as well. Integrating r squared will give us r cubed over 3, and we also need to add a constant to it. And now we integrate the other side. We'll call this constant 1. And if we integrate a constant with respect to t, we'll just get minus kt. And also there will be another constant here of integration. And this becomes r cubed over 3 plus kt. And I could write the other constants on the other side as 1, because c1 plus c2 is really just another constant c. Don't get put off by the fact that I didn't write minus c over here. I can do that. That'll be just a c. Well, now we do have a complete equation which links the radius with time, two constants in here, and one of them is the k and one of them is the c. Given that we are told that the initial radius of the balloon is 40 and after 5 seconds the radius of the balloon is 20, we can work out the k and the t. So we can say that from at t is equal to 0, our radius of the balloon is equal to 40 centimeters. So if we insert this into this equation over here, we'll have 40 cubed over 3 plus kt, where t is equal to 0, which is equal to c. And this will be 64,000 divided by 3, which is equal to c. As I don't want any decimals yet, I'll leave it like this. Now the second information we have is when t is equal to 5, our radius is equal to 20. So once again, let's put it into here. We know now what c is, by the way. So 20 cubed over 3 plus k, and what's 5k, is equal to 64000 over 3. And that will be 8,000 over 3 plus 5k is equal to 64000 over 3, where 5k is 56,000 over 3 and kk is 11,200 over 3. I chose to have this always over 3 because in my equation I've got r cubed over 3. So if I've got a k with a denominator over 3 and also a c with a denominator of over 3, it'll be easier for me to do the calculations. So can you see now I could multiply each one by 3, by 3 and by 3, and therefore I get rid of my 3's and I end up with having r cubed plus 11200t equals, and it would look nicer if I linked radius with time and write this on the other side. So it'll be 1 minus 11200t plus 64,000. And you are always required to write the exact answer, and this is the exact answer. If you were to round it, it will not be exact. So you would not be awarded any marks for writing 64,000 over 3 as 21333. And lastly, we are asked to find a limitation on the values of t for which this equation is valid. Well, this equation can only be valid when the radius of the balloon reaches to be 0. After that, there is no point in using this equation. So when the radius is 0, we'll just substitute that in, and we find that t is equal to 40 over 7. So that means that after the time 40 over 7 seconds, this equation does not work. Now you do not have to write that time is less than or equal to t is less than or equal to 40 over seconds because the model is only valid when r is greater or equal to 0. So it is enough for you to write down that limitation or invalid after t is greater than 40 over 7 seconds.